Welcome to Basics of Finite Element Analysis. Today is the fourth day of this week. Yesterday what we had discussed was temporal approximation approach which will help us convert an ordinary differential equation into a set of algebraic equations, and in that context we had discussed alpha family of approximations which help us convert derivative in time into differences of time. So today what we will do is we will use that approach to convert the ordinary differential equations which we had developed earlier, which are these, especially in context of parabolic equations. So this is basically temporal approximation. So we are continuing this discussion in today's lecture. Alpha family of approximations, it tells us that 1 minus alpha times velocity at sth time step minus alpha times time derivative at step number s plus 1 equals u of s plus 1 minus u of u at time step number s divided by time step s number s plus 1. Now what we do is we multiply both sides, pre-multiply both sides by delta t s plus 1 times a mass matrix. So what we get is 1 minus alpha delta t s plus 1 times mass matrix M times u at time step number s minus, so this is actually, this should be plus, so I get a plus sign here, plus alpha times delta t at s plus 1th time step multiplied by mass matrix M times derivative of time at time step s plus 1. So this is what we have done on the right side, and we do the same thing on the left side. This is what we have done on the left side, we do same thing on the right side. So delta t s plus 1 cancels away, and all what we have is mass matrix u at s plus 1 minus u at time step number s. So this is equation 1. Now we go back and look at this equation. Okay. And we have already said that for our case M2 is 0, and also we have said that K2 is 0. So what we can consider it as that this entire term is one single stiffness matrix, we call it K. So K is equal to K1 plus M naught. Okay. And M1 we call it as M matrix. So basically it is K times U plus M times U dot equals F. That is what? So we will use that terminology. So for parabolic system, the equations which we had developed earlier, they can be reduced to M times U dot, and these equations are valid at all time steps. So first I will write the equation at time step number s. So this is equal to M U dot plus K times U at sth time step is equal to F at sth time step. And then the equation is also true at the next time step. So, I will write that also m times u dot at time step number s plus 1 plus k times u at time step number s plus 1 equals f at time step number s plus 1. Please remember that these equations are at element level. We have not done the assembly of these equations. So, we have to develop these equations for each element at each time step. Okay. So, we call these equations 2a and 2b. So, that is equation 1, this is 2a and 2b. The other thing is we note that this m, so here we are assuming that m does not change with time. It does not change with time. That is what we are assuming, because typically in lot of systems m represents the mass. So, the mass of the system does not change at each element level also, it does not change with time. The stiffness may change, but mass does not typically change. So, what we do is that we put equations 2a and 2b in the LHS, which is this side of equation 1. Okay. So, in equation 1 we have m times u dot at s and m times u dot at s plus 1. So, we replace m u dot at time step s by fs minus k us from here, and we replace m times u dot at s plus 1 by f minus k u at time step s plus 1. Okay. So, what we get is, so we put 2a and 2b in 1, and what we get is 1 minus alpha delta t s plus 1. First I will have the force F minus K U, and all these are at s plus 1 plus alpha delta t s plus 1 F minus K U. Oh, so it should not be at s plus 1, it should be at time step s, and here I have time step s plus 1. And the right side becomes m times u s plus 1 minus u s. So, that is my equation 3. Okay. So, what is our goal? Our goal is to calculate u's at different time steps, right. So, if I know u at time step s, then I should be able to calculate u at time step s plus 1. Okay. So, that is my goal. I have to calculate times u, which is the nodal displacement at time step s plus 1 in terms of u at which is the nodal displacement at the last time step. So, if I know the initial solution, which is at time step t is equal to 0, then if I have this method, then I can figure out at time step 1, then in terms of time step 1 I can calculate solution at time step 2, and so on and so forth. So, what we will do is that we will collect all the variables at time step 1 on one side and all variables at time step s on other side, and then we will calculate the solution at time step s plus 1. So, I can express this entire equation in a compact form, and I call it k hat, and this k hat is evaluated at time step s plus 1. So, here it should be noted that now I am changing k also with respect to time, and this times primary variable vector at time step s plus 1 equals k hat times evaluated at time step s times u evaluated at time step s plus a force vector, and this is called f hat, it is different than f, and this is evaluated both at time step s and s plus 1, it depends on both. So, this is equation 4, and this equation 4 is gotten directly from 3, and because, and what is k hat? K hat at time step s plus 1 equals the mass matrix plus a constant A1 times k of s plus 1, okay, and k hat evaluated time step s, it is different, it is m minus A2 evaluated at time step s. Now, if k is not changing with time, then it does not matter, but here we have said that k, this k matrix, not k hat, it can change with time. If k is changing with time, then we have to calculate k hat at s and k hat at s plus 1, and we have to plug it in, and this equation 4 comes directly from 3 if we reorganize and rearrange these things, and here A1 is equal to alpha times delta t, that is s plus 1th time step, A2 equals 1 minus alpha times delta t, that is the sth time step, and finally, because here we also have this f hat vector, so f hat s comma s plus 1 equals delta time step s plus 1 times alpha f s plus 1 plus 1 minus alpha f s. Okay. So, all what we have done, how we have gotten all these equation 4, we have just reorganized equation 3 and given some different labels to, we have constructed a k matrix which is basically a combination of k hat at s, this k hat at s plus 1 is a combination of m and k of s plus 1, and same thing for k hat at s. So, this is there. So, once we have developed this equation, f hat is delta t corresponding to s plus 1th time step. We know all the time steps, how we are breaking up, so we know that. We know how is f changing with time, so I know f at s plus 1 and f at s. So, I can calculate f hat at s comma s plus 1. So, this term can be calculated at all times. U at time step s should be known, and k hat at s is m minus A2 k time k at s. So, again k hat at s is also known, k hat at s plus 1 is again m plus A1 times k s plus 1, this is also known. So, the only thing which is not known is u at s plus 1th time step. So, if we know u at s time step, then I can use this equation to calculate u at the next time step, s plus 1th time step. Okay. So, this is the temporal approximation. is the temporal approximation of the overall partial differential equation, and we are still at the element level. But what we have been able to do through this somewhat long process is that we have converted the partial differential equation first into an ODE and now into several algebraic equations. So, now the next two steps are fairly straightforward. What we have to do is we have to do assembly. We have to do assembly. Second, then we have to apply the boundary conditions, and then I start solving for u of s plus 1. I have to, and then I start solve for u at first time step. For that I have to know u at 0, otherwise if I do not know this side, then I cannot solve. So, this information comes through initial conditions. Okay. Once I have calculated u1, then I calculate u2, which is at the next time step in terms of u1, then I calculate u3 in terms of u2. So, in this way I keep on marching ahead in time, and at each point of time I calculate the solution in terms of the solution which existed in the last time step. So, when I am starting the process, I have to know what is the solution at the beginning, otherwise I cannot solve the for use at the end of first time step. So, that is why initial conditions become important, and what we see is that because our original partial differential equation had only first derivative in time, so we need only u0, which is one set of initial conditions. We do not necessarily need to know the velocity and others. So, we need only one set of initial conditions, because the original differential equation had only first order derivative in time. So, that is the overall process for solving hyperbolic equations, and I hope that you would be able to use this, and you can read a little bit more about this from the textbooks which I have discussed, I mentioned earlier, or through other texts. So, this completes our discussion on parabolic equations, I am sorry, not hyperbolic, parabolic equations, and tomorrow we will cover and develop a similar method for hyperbolic equations. So, that concludes our discussion for today, and we look forward to seeing you all tomorrow. Thanks.